Hello everyone, today we are going to discussing about GPU coprocessing. What is GPU coprocessing? Graphic Processing Unit GPU were originally engineered for rendering stunning visuals in gaming and graphic application. Today they have evolved into powerful coprocessor that accelerate parallel computational tasks across countless industries. CPU versus GPU. CPUs and GPUs are designed for different types of tasks. A CPU has a few powerful cores and is optimized for sequential processing and complex control tasks. A GPU contains thousands of smaller cores and is designed for massive parallel processing of similar operation. When CPUs and GPUs work together, they complement each other. How CPU coprocessing works. CPU control layer. The CPU handles general program, control flow, sequential logic, and task orchestration across the system. Data transfer. Input data is copied from system memory to GPU memory via the PCIe bus interface. Parallel execution. The GPU executes compute-intensive parallel tasks using thousands of cores simultaneously. Result return. Process result are transferred back to CPU memory to finalize process the output. Real world application in parallel and distributed computing. AI and deep learning. Training complex neural networks order of magnitude faster using framework like PyTorch and TensorFlow. GPU acceleration has made modern AI breakthrough possible. Scientific simulations. Modern complex system including weather patterns, molecular dynamic physics simulations and genomic research with unprecedented accuracy and speed. Challenges in GPU coprocessing. Memory limitation. GPU memory capacity is limited compared to system RAM, requiring careful data management strategies when working with enormous data that exceed available GPU memory. Data transfer bottlenecks. PCIe bus bandwidth constraints can create perform bottlenecks when frequently moving large amount of data between CPU and GPU memory spaces. Programming capacity. Optimizing code for parallel execution requires specialized skills and understanding of GPU architecture, memory hierarchies, and thread management paradigm. Advantages of GPU coprocessing. Enhancing computational speed and performance. GPUs can process thousands of tasks simultaneously due to their massive number of cores, dramatically reducing execution time for data intensive operations like machine learning, scientific simultaneously, and big data analytics. High throughput. GPUs are optimized for high throughput processing a large volume of data in a given time rather than low latency for single task, making them ideal for tasks that can be broken into many small repetitive operations. Advantages of GPU coprocessing. Scalability. System can scale effectively by adding more GPUs or leveraging cloud-based GPU instance, enabling linear speedups for demanding workloads without a complete overhaul of existing infrastructure. Energy efficiency. For appropriate parallelizable tasks, GPUs achieved more performance per watt compared to CPUs, leading to potential cost saving in large data centers by requiring less hardware and cooling. Advantages of GPU coprocessing. Resource utilization by offloading highly parallelizable tasks to the GPU. The CPU is freed up to manage sequential tasks and operating system function efficiently, maximizing overall system hardware utilization. Cost effectiveness for specific tasks. For specific high performance computing tasks, GPUs can be a more cost effective solution than building large clusters of high end CPUs. Disadvantages of GPU coprocessing. Limited single thread performance. Individual GPU cores are simpler and less powerful than CPU cores, so they perform poorly on tasks that are sequentially cannot be parallelized or involved complex branching logic. Programming complexity. Fully utilizing a GPU power requires specialized programming knowledge and framework like NVIDIAS, CUDA, are the open standard OpenCL, which is more complex than standard CPU programming. Disadvantages of GPU coprocessing. Memory constraint and transfer bottleneck. GPU memory VRAM is typically limited in capacity compared to system RAM, which can be a bottleneck for extremely large dataset. Additionally, data transfer between the CPU and GPU via the PCA bus adds latency and can slow down overall performance if not managed efficiently. Power consumption and heat. High performance GPU consume substantial power and generate significant heat, which increase operational cost and require robust cooling solution in data transfer. Disadvantages of GPU coprocessing. Application compatibility. Not all algorithms or applications are suitable for GPU acceleration. Some are better suited for CPU processing due to their intrinsic nature or data dependency. Synchronization issue in distributed environment. In a distributed system, coordinating tasks and managing data dependency across multiple independent GPU or CPU nodes can lead to synchronization challenge and increase network traffic if not careful engineered. Conclusion. Transformative computing GPU coprocessing revolution performance by combining CPU flexible with GPU parallel processing power, enabling breakthrough, accelerating innovation in AI, scientific research and data analytics that were previously impossible. Future ready infrastructure. Investing in GPU coprocessing today prepare your organization for tomorrow computational challenge.